Okay, so the comparison test is, there are two of them. All right, and so we can use these tests to determine whether or not a series converges or diverges by comparing them to other series that we know that converge or diverge. Okay, so the first of these is the direct comparison test. All right, so that's going to be test number 6. Okay, so the direct comparison test, we are directly comparing two different series terms with each other. Okay, so I'm going to have two series. So let's let summation AN and summation BN be series such that they're positive term series. AN is less than or equal to BN for all n, for all little n after some big N. Okay, so it may not happen in the beginning, but as we look at the series overall, we can see, that's too much. We can see that one series always is bigger than the other. Okay, two things will happen. One, if the bigger series converges, so if the summation of Bn converges, then the summation AN also converges. So if I'm smaller than something finite, then I'm finite. Then the second one is the summation AN diverges. Then the summation BN also diverges. So if I'm bigger than something that goes to infinity, I also go to infinity. Okay, so what do we know about the harmonic series? Does anybody remember the harmonic series? Okay, so here's the first series I want to look at. It is the summation n equals 2 to infinity of 1 over n minus 1. Okay, now this kind of looks like the harmonic series. All right, the harmonic series starts off with 1 plus a half plus a third plus a fourth. Well, this one is starting off with a half plus a third plus a fourth. So the only difference between this series and the harmonic series is the very first term, actually. Okay, so I know that if I could see, since this kind of looks like the harmonic series, and I know the harmonic series diverges, I'm thinking this might diverge. Okay, so here's the thought process. So this series, the summation, n equals 2 to infinity of 1 over n minus 1 is 1/2 plus 1/3 plus 1/4 plus ... So it looks like the harmonic series. And the harmonic series converges. I'm sorry, diverges. So I'm thinking this might also diverge. But that's not good enough. We have to prove it. Okay, so the way to prove it is to see if I can get this related to the harmonic series. So I know that n minus 1 is always less than n. So that means 1 over n minus 1 is always bigger than 1 over n. Okay? If n minus 1 is less than n, then 1 over n minus 1 is bigger than 1 over n. So now let's let an be the series 1 over n, and bn be the series 1 over n minus 1. An is always less than bn. I also know that's wrong. That's right. An is always less than bn. And the summation of an, which is the summation of 1 over n, which is the harmonic series, diverges. So by the comparison test, by the direct comparison test, the summation n equal 2 to infinity of bn equal to the summation n equal 2 to infinity of 1 over n minus 1 also diverges. Okay. Any question about that? Okay. Here's another example. The summation n equal 1 to infinity of 1 over n squared plus 6. Now, if I didn't have the 6 there, so for large n, one over n squared plus 6 kind of looks like 1 over n squared. Because if n is like 100,000, then that little 6 doesn't quite really matter. So they kind of look alike, all right, for large n. Now, again, my thought process, so I'm thinking, the summation n equals 1 to infinity of 1 over n squared converges by the p-series test here p is equal to 2, which is greater than 1. So that converges. So I'm thinking, okay, so I might guess that the summation n equals 1 to infinity of 1 over n squared plus 6 also converges. So I have to prove that. Okay, so that requires some work. Okay, so let's think about this. So let's start off with n squared plus 6 is bigger than n squared. So therefore 1 over n squared plus 6
You mommy?
1 over n squared plus 6 is less than 1 over n squared. So now I'm going to let an be the 1 over n squared plus 6. And I'm going to let bn be 1 over n squared. So now I can see that an, which is equal to 1 over n squared plus 6, is less than 1 over n squared, and that's equal to bn. So an is less than bn. So an is less than bn, and the summation n equals 1 to infinity of 1 over n squared converges. By the p series. So by the direct comparison test, the summation n equals 1 to infinity of 1 over n squared plus 6 also converges. So the direct comparison basically says, I'm younger than you or I'm older than you. I'm smaller than you or I'm bigger than you. Okay, it is comparing the quantity size of the terms of the series. And if you can show that the series, one series is, all its terms are smaller than a series that converges, it will converge. And if you can show that all of its terms are bigger than a series that diverges, it also diverges. Okay, any questions about that? Okay, so you have to do whatever you can to try to make it look like whatever you need it to look like. Okay. Here's another example. This one's more difficult. Summation n equal 1 to infinity of 1 over n factorial. Now, this is a hard one to be able to show whether it converges or diverges, but this one does converge. And the easiest way to show it converges is, again, compare its terms to the terms of a sequence that we know converges. So what do these terms look like? This looks like 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial, etc., etc. Now, I'm going to keep adding every time I keep adding a little bit, but does this eventually become a finite sum? That's what I'm trying to guess. All right. So these terms are actually equal to 1 plus a half plus 1 over 6 plus 1 over 24 plus 1 over 120 plus ... So now it would be nice if I could find some series that I know that already converges or diverges, whichever it's either bigger than something that diverges or smaller than something that converges, and that's what will help me. Now I can see these are very, very small. So clearly these terms right here, I can't tell whether they're bigger or smaller if I were to try to look through and do the harmonic series. But we did do one that looks similar to this. I know that 1 is equal to 1. 1/2 is equal to 1/2. But 1/6 is certainly less than 1/4. And 1/24 is certainly less than 1/8. And 1/120 is certainly less than 1/16. So each one of these terms appears to be smaller than a power of 2 to the n. Okay, well, 1/2 to the n. So this one is simply 1/2 to the 0. This one is 1/2 to the 1. 1/4 is 1/2 squared. 1/8 is 1/2 cubed. So I can see that each one of these individual terms is less than the terms of this series. So this is less than 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... So this is the sum, n equals 1 to infinity, of 1/2 to the n minus 1. Now that's a geometric series. So this right here, we already know. That's a geometric series. Where the absolute value of r equal to the absolute value of 1/2 is less than 1. So we know this converges. Okay. So since the summation n equals 1 to infinity of 1 over n factorial is less than this series, the summation n equals 1 to infinity. We actually already know what this series sums to, 1/2 to the n minus 1. We already know that that sums to 2. That implies then that the summation n equals 1 to infinity of 1 over n factorial converges. I don't know what its sum is, but I know its sum is finite. Okay, so these are, that's the direct comparison test, making sure it is smaller than something that converges or greater than something that diverges. Okay, any questions about the direct comparison test? Okay. Next test. Number 7. This is the limit comparison test. Okay. All right, so the limit comparison test has 3 parts to it. I hope you're good at limits because you're going to need to be taking limits for the limit comparison test. And the limit comparison test works even when the direct comparison test does not. Okay, so suppose that summation AN and summation BN are series with AN is positive and BN is positive. And this is true for all n bigger than or equal to some n. So that means at some point in the series, it has to be true. May not be true in the beginning, but as it moves forward out towards infinity, all the terms are positive. So here's the first criteria. If the limit as n approaches infinity of AN over BN is equal to some number L, then summation AN and summation BN both converge or both diverge. Okay, number 2, if the limit as n approaches infinity of AN over BN is equal to 0 and the summation BN converges, then summation AN converges. That doesn't even look like a summation. That look crazy. Okay. And then the third criteria is if the limit as n approaches infinity of AN over BN is equal to infinity and the summation of BN diverges. Then the sum. Okay, wait a minute, something's wrong. Then summation AN diverges. Okay. Okay. So we looked at this one here, the summation of 1 over n minus 1. Okay, so now let's take a look at this one. So the summation n equals 1 to infinity of 1 over two n plus 1. Okay, so now as I look at this one, again, if n gets really big, that 1 kind of doesn't matter. All right, so if that 1 doesn't matter, I kind of look like 1 over n again. So I'm thinking it might do the same thing. So let's pull out the 1/2 for a moment. So I'm gonna factor out the 1/2. And that gives me the sum n equals 1 to infinity of 1 over n plus 2. No, it does not. It gives me 1 over n plus 1/2. Okay, so up there I said, let's look at the relationship between n plus 1/2 and n. So n plus 1/2 is certainly bigger than n. And so 1 over n plus 1/2 is less than 1 over n. And now I have the summation of 1 over n. I know that blows up, but this is smaller than something that blows up. So this doesn't help me. Okay, so nope, this doesn't help me at all. Okay, and the reason why is because this is smaller than a divergent series. So that doesn't help. Okay, so since this doesn't help, put that back. Let's try to limit comparison. So the direct comparison doesn't work. All right, so direct comparison doesn't work. So let's try to limit comparison test. Now, again, I still think it diverges. So let's use the limit comparison test with the summation n equals 1 to infinity of 1 over n. So now I already know this diverges. So let's look at an is going to be 1 over n plus 1/2, and bn is going to be 1 over n. So I look at the limit as n approaches infinity of an over bn. So that's the limit as n approaches infinity. An is 1 over n plus 1/2, and that's divided by 1 over n. So that's the limit as n approaches infinity of n over n plus 1/2. I'm going to use L'Hopital's rule. Oh, let me before I use L'Hopital's rule, let me show that you get infinity over infinity. So now I'm going to use L'Hopital's rule. So this is the limit as n approaches infinity. The derivative of the top is 1. The derivative of the bottom is 1, and that equals 1. I get a finite number. That number right there is L. L is finite. So that says they both do the same thing. So they both diverge. Okay. Here's another one. Number 2. Summation n equal 1 to infinity of the square root of n over n squared plus 3. Okay. So what does this look like for large N? So for large N, we get the square root of N over N squared plus 3 just looks like the square root of N over N squared plus 3 over N squared. But that is N to the 1/2 divided by N squared. So that looks like 1 over N to the 3/2 power. Okay, so that's what that kind of looks like. Did everybody see how I did that? I said, if N is really, 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 really big, really, if I have $15 million and I'm going to be upset over 3 cents, not really. Okay, so if N squared is 15 gazillion billion or whatever it is, and am I worried about the 3 cents? Not really. It's not adding a whole lot to the pot. So I'm seeing that it's not, that 3 really doesn't make that much of a difference. So I can show that this thing kind of looks like 1 over N cubed, N to the 3/2. So let's use the limit comparison test for that. So we're going to let AN be the square root of N over N squared plus 3. And we're going to let Bn equal 1 over N to the 3/2 power. Okay, so now I'm going to get the limit as N approaches infinity of AN over Bn. That's the limit as N approaches infinity. AN is the square root of N over N squared plus 3. And when you divide by a fraction, you multiply by the reciprocal. So you get N to the 3/2, obviously over 1. I'm only writing that for those who need to see it. So this is the limit as N approaches infinity. So this right here is AN, and this is 1 over Bn. Okay. This is AN, and this is 1 over Bn. Okay. So therefore, I get N to the 1/2 times N to the 3/2 over N squared plus 3. So that is the limit as N approaches infinity of N squared over N squared plus 3. Now, you can do L'Hopital's rule twice, all right? Because this is infinity over infinity. So L'Hopital's rule the first time is going to give you the limit as N approaches infinity of 2N over 2N. Oh, actually, we only need to do it one time. And that's 1. Okay. And 1 is finite. So therefore, they both converge or both diverge. Can somebody tell me what do they do? Do they both converge or both diverge? And tell me not only how you, what you think the answer is, how did you get it? And while you guys are thinking that through, I am going to take roll. Let's see who's here. Okay, so can somebody tell me whether this converges or diverges? Whether my original series converges or diverges? Nobody has any idea.
And this is gonna be kind of a guess, but I was thinking would it be kind of convergent? So sorry, or I thought it would be convergence for
You think it converges? Why?
um. I was thinking because the limit was more of a finite number than, or if the limit was a finite
Again,
number, and
they both converge. Why?
I coughed twice and hiccuped.
oh, sorry.
Okay, Victor, why are you say they both converge?
I was saying that it was a since the limit of the that we take from the test was a finite number or one was less than infinity. So based on that, I thought that both like the values of which would actually converge.
Okay.
Or there be a limit to the.
All right, so I'm glad that you said that because that is a common misconception. Just, okay, so this is where life gets scary and because it gets all starts to come together. Just because you get a finite number doesn't mean it converges. For this particular test, when you get a finite number, it means that when you get a finite number, it means they both converge or diverge. So you have to go back and look at, okay, Logan, you're making too much noise there. All right. You'll have to go back and look at the series we compared it to. That's this. We compared it to this.
Okay.
Okay. So when I say they both converge or they both diverge, you go back and look at the series we compared it to. So it was compared to the summation n equals 1 to infinity of 1 over n to the 3/2. Now, does that converge or diverge? Obviously, I should say it converges because I accepted your answer that it does converge. So yes, this converges. Why does this series converges? Which converges? By what? Why does that converge?
The value of the limit wasn't would it be into the 3/2 or it's converging to
You're right.
sorry.
You're right. P series. P series, P is equal to a half, 3/2. Okay, you guys have got to study this stuff as it is coming or you are going to have a headache. Because it's a lot. Okay, any questions so far? Okay, I'm gonna give you another one. How many did I do in this section? Only did 2? Let me do another one. Oh, that's a good one. Okay. So I want to use the limit comparison test. What am I going to compare this to? What series am I comparing it to? Okay. We're going to
Got
compare
this.
to n equals 1 to infinity of 1 over 2 to the n. Okay. That series, 1 over 2 to the n.
Would that be P series?
Now, that's not a P series.
Okay.
Okay, almost. Okay, so now this series is 1/2 plus 1/4 plus 1/5. No, it's not. Plus 1/8 plus dot, dot, dot. So this series, if I factor out a 1/2, this series is equal to 1/2 times the sum n equals 1 to infinity of 1 over 2 to the n minus 1. Okay, so whoa. Okay. So that series is just 1/2 of the geometric series. Okay. Which is 1/2 summation n equal 1 to infinity of 1/2 times 1/2 to the n minus 1. Okay, so that is just, so this is a geometric series. R is equal to 1/2. So it converges. And that kind of, they look, see how, do you guys see how they look alike? See how this looks like that? See how they look alike? And if n is really, really big, we don't care about that minus 1. So they kind of virtually look alike. So then I'm going to take the limit as n approaches infinity of an over bn, where an is 1 over 2 to the n minus 1, and bn is 1 over 2 to the n. Okay, so therefore, let's check the limit. So this limit as n approaches infinity of an over bn is going to be the limit as n approaches infinity of 1 over 2 to the n minus 1 divided by 1 over 2 to the n. So that's the limit as n approaches infinity of 2 to the n divided by 2 to the n minus 1. Okay. So I'm going to divide this one. If you use L'Hopital's rule, you can use L'Hopital's rule on this one. Oh, this is a good one to use L'Hopital's rule. This one gives you infinity over infinity. Okay, so if I use L'Hopital's rule, what's the derivative of that? The limit as n approaches infinity. What is the derivative of 2 to the n? You get 2 to the n natural log 2. And in the denominator, you're going to get 2 to the n natural log 2. And that's 1, which is less than infinity, it's finite. So therefore, since this one converges, all right, that we use the fact that they either both converge or they both diverge. So they both converge. Okay, any questions about that?
Can you scroll up a little bit?
I can. Scroll up to here.
Right there is fine.
Okay.
Thank you.
You're welcome. Okay, let me see.